Hey everyone, and welcome to this deep dive. It's all about fusion energy. You know, fusion energy is a pretty hot topic these days.
Yeah, it really is.
And you're really interested in getting a handle on the waste produced by fusion, compared to fission,
Right.
as well as those recent advancements from MIT and CFS.
Right.
They're pushing the boundaries of fusion tech with smaller, more efficient magnets.
Yeah, that's one of the big things.
It's pretty exciting stuff, right?
Absolutely.
We've got some dense material to get through today.
Yeah.
But don't worry, we'll break it down together.
Yeah, I think it's a complex topic,
Yeah.
but I think we can shed some light on it.
Yeah, for sure.
And it's important to start with the fundamentals. What exactly is nuclear fusion?
Yes. Let's get back to basics.
Yeah.
I know it's the process powering the sun, but I'm a little fuzzy on the details.
Okay.
How does it differ from fission,
Yeah.
which is what we use in today's nuclear power plants?
You're right. Fusion is what makes stars shine. It involves fusing together lighter atoms like isotopes of hydrogen to create helium, which releases massive amounts of energy.
Okay.
Fission, on the other hand, splits heavier atoms like uranium to release energy.
Okay, so they're basically opposite processes,
Yeah,
but both result in energy release.
exactly.
Now, fusion is often talked about as this, clean energy source,
Right.
but you were mentioning that it does produce some radioactive waste.
Yeah,
Can you elaborate on that?
absolutely.
That's something I'm really curious about.
While fusion doesn't produce the same long-lived, high-level radioactive waste as fission, it's not entirely waste-free.
Okay,
The type and amount of waste are significantly different, though.
got it.
Fusion reactions primarily generate low to medium level radioactive material, which decays much faster than the high-level waste from fission.
Oh, okay, so that means the waste issue is less problematic with fusion compared to fission?
Precisely.
Okay.
Think years instead of millennia when it comes to the decay time of fusion byproducts.
Oh, wow.
It's worth noting that research is ongoing to further reduce the activation of materials in fusion reactors and explore possibilities for recycling components, making the waste issue even more manageable.
That's reassuring to know.
Yeah.
And speaking of advancements,
Mm.
MIT and CFS are making waves with their innovative approach to fusion technology,
Right.
especially their work on smaller, more efficient reactors
Mm-hmm.
using these high-temperature superconducting magnets.
Yes.
What exactly are those, and why are they so significant?
Yes. The HTS magnets. They
Yeah.
really are a game changer.
Okay.
The challenge with fusion is containing the incredibly hot plasma,
Right.
which requires incredibly strong magnetic fields.
Yeah.
Traditional magnets, while powerful, are massive
Yeah.
and consume huge amounts of energy.
Right.
HTS magnets can generate those same strong fields, but in a much smaller footprint.
So it's all about making things more compact and efficient.
Exactly.
I can see how that would be a big deal.
This breakthrough allows for the construction of smaller fusion devices like SPARC, which is MIT's experimental reactor designed to demonstrate net energy gain from fusion.
Wow.
So,
Okay, so that's a good transition
yeah,
because they're aiming for net energy gain by the middle of the decade, right?
that's right. And that's where their ambitious timeline comes into play.
Right. They're aiming for net energy gain by the middle of the decade,
Yeah, middle of the decade, 2025.
2025. Okay, so what exactly does net energy mean in this context? I remember it being mentioned before, but I'd love a little refresher.
Essentially, it means producing more energy from the fusion reaction than what's required to initiate and sustain it.
Right. Okay.
So you're putting in some amount of energy to get it going,
Yeah.
but then you're getting more out.
Yeah, okay.
It's a crucial milestone because it demonstrates that fusion can be a viable source of power.
It's like finally breaking even,
Exactly.
proving that fusion can actually deliver a surplus of energy.
Precisely. It would be a monumental achievement, kind of like fusion's Kitty Hawk moment, as they put it.
Right. Oh, yeah. Marking a significant leap forward in the field.
Yeah, I remember them drawing that analogy in the video.
Right.
That comparison to the Wright brothers' first flight really highlights the potential impact, doesn't it?
Yeah.
It's not just about a scientific breakthrough. It's about opening doors to a whole new era of energy.
Exactly. And what's really fascinating is the innovative approach they're taking to achieve this vision. It's not just about scientific advancements. It's also about organizational innovation.
Okay.
Their partnership with CFS, a startup, is a testament to their commitment to accelerating the transition from research to practical application.
Yeah, that collaboration struck me as well. It seems like a really smart strategy.
Yeah.
By teaming up with a nimble startup, they can move much faster than traditional research institutions might.
Absolutely. It allows them to leverage the agility and speed of a startup while also Benefiting from the expertise and resources of a renowned institution like MIT, this kind of cross-sector collaboration could be a game changer for the development of fusion energy. It's like combining the best of both worlds.
Exactly.
So with this accelerated process and these downscaled magnets, it seems like they're on a fast track to making fusion a reality.
It seems that way.
What are some of the challenges they still need to overcome to reach that goal of net energy gain and eventual commercialization?
Well, even with these advancements, there are still technical hurdles to clear. One key challenge is maintaining the stability of the plasma for extended periods.
Right.
They need to ensure the fusion reaction can be sustained long enough to achieve a meaningful energy output.
That makes sense. It's like keeping a delicate balancing act going, right?
Yeah.
And I imagine that developing materials that can withstand the extreme temperatures and pressures inside the reactor is another ongoing challenge.
You're absolutely right. Finding materials that can handle those conditions for prolonged periods is crucial for the durability and reliability of fusion reactors. But researchers are actively working on solutions, exploring new materials and designs.
So it sounds like a combination of scientific ingenuity and engineering prowess is needed to crack this fusion puzzle. And then there's the whole question of scaling it up.
Right.
Even if they achieve net energy with SPARC, how do we go from a small experimental reactor to something that can power cities or even countries?
That's a crucial question, and one that researchers are already thinking about. The modular design of these smaller reactors could actually make scaling up easier. Instead of building one massive complex power plant, you could have multiple smaller reactors working together, kind of like building blocks of clean energy.
That's a really interesting concept.
Yeah,
It seems much more manageable and adaptable than trying to construct a single gigantic facility.
for sure.
And with the focus on efficiency and scalability, they're setting the stage for a future where fusion energy could become a truly impactful solution to our energy needs.
Precisely. And with the pace of innovation accelerating, it feels like we're on the cusp of a major breakthrough in fusion energy. It's an exciting time to be following this field.
It really is. We've covered a lot of ground today, exploring the waste issue, the advancements in magnet technology, and the innovative approaches being taken to accelerate the development of fusion energy. But before we wrap up, I want to touch on something we haven't discussed yet.
Okay.
The potential downsides or risks associated with fusion. We'll delve into that and more in the final part of our deep dive.
That's a crucial aspect to consider. We'll explore the potential challenges and risks, as well as the broader implications of fusion energy for the world.
Okay, so we're back
Back for round 3.
for the final part of our deep dive into fusion energy.
Exactly.
We've covered a lot of ground so far.
We have.
From the waste issue to the incredible advancements being made with HTS magnets
Right.
and the innovative strategies being employed by MIT and CFS.
Yep.
But before we wrap up, I think it's important to talk about potential downsides or risks associated with fusion energy.
Okay.
Are there any concerns we need to consider even with all the positive developments?
That's a great point. While fusion energy holds immense promise, it's crucial to approach it with a balanced perspective and acknowledge potential challenges.
So what are some of those challenges? What are the potential downsides we need to be aware of?
One aspect often raised is the cost building these fusion reactors, even the smaller, more efficient ones, requires significant investment. The initial cost of developing and deploying fusion energy infrastructure could be substantial.
That makes sense. It's a cutting-edge technology, and those kinds of advancements often come with a hefty price tag. But wouldn't the long-term benefits potentially outweigh those initial costs?
Absolutely. When considering the economics of fusion energy, we need to look at the bigger picture. Unlike fossil fuels, which are finite and often geographically concentrated, fusion fuel is readily available and practically limitless. This could lead to greater energy independence and price stability over time.
So it's about shifting our perspective from short-term expenses to long-term gains. And let's not forget the environmental benefits, which surely have economic implications as well. No greenhouse gas emissions, significantly reduced radioactive waste. Those factors have to be part of the equation.
Precisely when we factor in the long-term costs of climate change mitigation and the health impacts associated with fossil fuel pollution, the economic case for fusion becomes even stronger. It's an investment in a cleaner, more sustainable future.
Okay, so cost is a factor, but potentially outweighed by the long-term benefits.
Right.
What about safety? I know we touched upon the differences in waste,
Hmm.
but harnessing the power of the sun still sounds inherently risky.
Yeah.
Are there safety concerns with fusion reactors?
It's a valid question. It's important to understand that fusion reactions are fundamentally different from the uncontrolled chain reactions that occur in nuclear weapons.
Right.
Fusion reactors operate under highly controlled conditions with multiple layers of safety mechanisms.
So we're not talking about a Chernobyl-type meltdown scenario.
No, the likelihood of such an event is extremely low. The plasma in a fusion reactor is inherently unstable. If any of the control systems fail, the plasma simply cools down and the reaction stops. It's a self-limiting process.
That's reassuring to hear. It sounds like safety is being prioritized in the design and operation of these reactors.
Absolutely. The researchers and engineers working on fusion technology are keenly aware of the importance of safety and are constantly working to ensure the highest standards are met.
This has been an incredible deep dive. We've explored the science, the potential, and even the challenges associated with fusion energy. I feel like I've gained a much deeper understanding of this complex and fascinating field.
It's been a pleasure unpacking this topic with you. It's clear that fusion energy holds immense potential to revolutionize our world, and the progress being made is truly inspiring.
And even though there's still hurdles to overcome, it feels like we're on the verge of a major breakthrough. Who knows? Maybe in a few years, we'll be talking about fusion power plants being built around the world.
That's certainly a possibility. The pace of innovation is accelerating, and with continued investment in research, fusion energy could become a reality sooner than we think.
It's an exciting future to contemplate. Thanks for joining us on this deep dive into fusion energy. We'll see you next time for another exploration of a fascinating topic.